Alright, okay, so what we want to look at now would be a topic of triple integrals. Alright. Okay, so for triple integral, what we're going to be doing now is we're going to be integrating over a solid region in three-dimensional space, right? So, okay, so our notation for triple integral, this is our notation for triple integral. This here is the notation for triple integral. So you see in your three integration signs, you're integrating some function, right, that's defined in three-dimensional space, right? And then you're integrating over some particular region in three-dimensional space, such as this solid box here, right? Okay, so by a solid box here, I don't mean the surface, I don't mean the sides, right? What I mean is this box over here and the interior of the box, right? So you could consider this, say, for example, as being, say, like a solid metal cube, right? So it's not just the shell, it's not just the outside. I'm concerned about what's going on the inside of this box too, right? So what I want to do is I want to integrate over a region that's solid, right, in three-dimensional space. Now the types of regions that we're going to look at in this class for triple integrals, right, would be fairly two simple cases, right? One case where it's a solid rectangular box, and this is a particular case where it's a solid cube. I can in fact change the right. So it doesn't need to be a cube. It can be a solid rectangular box where the side lengths are all not just the same, right? So for example here, if you want the width over here is 2, right? Your height is 1. Okay, so your height is 1, and your length is 3, right? Okay, right. So anyway, so one type of region that we're going to be finding triple integrals, where we're going to be evaluating triple integrals, right? So evaluating triple integrals over a solid region in three-dimensional space, right? One possible type of region that we will look at would be a rectangular box. Next type of region would be cylindrical solids, right? So for example, this here, this is a cylindrical solid. And we saw something like this already, right? But the cylinders that we were looking at previously was actually the surface of the cylinder, right? Now, what you want to do is we're considering this to be a solid cylinder, right? So, if, for example, say you have like a pipe, so on, right? That's and you cut a section of your pipe, and you say you fill it with concrete or something like that. Then what you'd get is you get something solid, right? So we're going to be integrating over something as solid, right? So not just the surface, but the interior as well too, right? Okay, and this cylindrical solid, how we're going to work this out is we're going to work with cylindrical coordinates, which would be just a minor generalization of polar coordinates, right? But we will eventually get to that, right? The main thing is that the two types of regions that we're going to look at would be cylindrical solids like this over here that's centered around your z-axis. And solid rectangular boxes like this, right? And the solid rectangular boxes that we would look at, right? The sides are going to line up with your x, y, and z axes, right? So it's not to say that this cylinder is, say, offset and rotated by a certain amount, right? The edges of your cylinder would line up, well, at least be parallel to x, y, and z axes, right? Okay, so as I said, we're going to be integrating over those types of cylindrical solids, right? And let me first give you a motivation as to what your triple integral is working out for you, right? Okay, right, so suppose I have a metal cube that is of side length 2, right? So Okay, so this metal cube is it has each side, the length, the width, and the height is 2, right? So what you have is a cube here, right? Okay, so this is a metal cube of side length 2. The volume is going to be 2 times 2 times 2, which is 8, right? So this has volume 8, right? And if this has, say, a constant density of 2.5, right, then you know that the mass is equal to the density times volume, right? Assuming that the density is constant throughout, right? Okay, and if the density is constant throughout at 2.5, right, then the mass is equal to density times volume, which is 2.5 for the density, and the volume of the cube turned out to be 8, right? So this will work out to be 20, right? Okay, so that's an easy calculation for getting mass given your density and the volume, right? Okay. Now, what we want to do is we want to consider, say, a somewhat more complicated situation where your density is no longer going to be uniform throughout your solid, right? Okay, so this would be how you describe a variable density, right? And this is similar to what we did for surface area density. Okay, where your surface area density could actually vary from point to point, right? But this is a simpler concept. This is just now normal density, right? Density in a normal sense. So what this is saying is that the density of this cube here is going to change according to the z, right? So when the z is equal to 0, you're going to have density of 1. Okay, so when your z is equal to 0, right, you will have a density of 1. And then when z is equal to, well, the height over here is 2, right? So when the z is equal to 2, the density over here is going to be 5, right? Okay, so your density is increasing linearly with height over here, right? So it's starting at 1 over here and then going up to 5 over here, right? What we want to do is we want to get the mass of this solid metal cube, right? Given the fact that the density is just changing drastically from 1 over here to 5 to the top, right? Okay, and in order to work that out, right, in order to get the mass in this case, what you do is you use a triple integral, right? So you could regard this situation as being an interpretation of your triple integral, right? So if you working out a triple integral, you're going to be integrating over some solid region, right? And the solid region, capital B in this case, is the solid cube, right? You're going to be integrating over you're going to be integrating a function over that solid region, right? And the function is changing possibly changing values for different points in your solid region, right? And you see in this particular function over here, it is changing values from point to point, right? When you start on the bottom, the function value is 1, and when you get to the top, the function value is equal to 5, right? Okay, so this function over here is changing values, could potentially change values in your solid region V, right? And what you want to do is basically you summing up your function values over your solid region B over here, right? Okay, and as I said, right, if you're regarding this function over here as just density, right, then what you're going to be doing when you work out your triple integral where your function over here is density, when you work out your triple integral for a density function over here over your solid region B, right, what you're actually calculating is you're calculating the mass of this object B, right? Just as how you calculated the mass over here. In this case, it was pretty easy because the density was constant. In this case, it's not that easy, right? Because the density is changing now, right? And if the density is changing now, what you need to do is you need to work it out via triple integral, right? Okay, so let's actually, before I get into like the formal procedure of or giving you a formal definition of a triple integral or how you work this out, right? We can actually just calculate it right here, right? Okay, so this is a triple integral, right? And it's in variables x, y, and z, right? Let me just quickly remind you what we did for double integrals over a rectangular region, right? So I had this double integral over a rectangular region, and the rectangular region was the x was lying between 3 and 4, and the y was lying between 1 and 2, right? Okay, so what we're doing is we're integrating this particular function over here, this xy plus ey, right? Okay, and we're integrating over this rectangular region, right? So your rectangular region is this rectangular region in the xy plane, right? This is a three-dimensional picture, right? Okay, and three-dimensional space, so your region R would look, say, slanted like this. Remember, this region R is in the xy plane, right? So it looks a little slanted because this is a picture of your three-dimensional space, right? So you have a certain amount of perspective going on, right? Anyway, so this is your region R, rectangular region, and what we're doing for a double integral is we're integrating over this rectangular region, right? And when we integrate over a rectangular region, right, what we're going to do is we're going to integrate with respect to your variables, right? So we're going to integrate with respect to y and then with respect to x, right? Now, what I have here, right, is in this three-dimensional case, right, I'm integrating over a three-dimensional region, right? Over here, for your double integral, right, what you were integrating over was this two-dimensional region over here, right, in the xy plane, right? Now, what I'm integrating over is a three-dimensional solid region here, right? Specified by this, that the x lies between 0 and 2, the y lies between 0 and 2, and the z lies between 0 and 2, right? Okay, so if you want the, you see in here that the x is lying between 0 and 2, right? Probably better way to put my x-axis like this, right? So the x is lying between 0 and 2, right? The z is lying between 0 and 2, and the y is lying between 0 and 2, right? Okay, so similar to what we had for a rectangular region, now this is a rectangular box, right? So you have x line between two constants, y line between two constants, and z line between two constants, right? Okay, and we're going to integrate in a similar manner to what we did for your rectangular case, right? So for your double integral, right, what did you do, right? You had that the x was lying between 3 and 4 and the y was lying between 1 and 2, and you use those as your limits, right? 1 and 2 for the y, 3 and 4 for the x, right? And you're integrating twice, right? In this case, you're going to be integrating 3 times, right? You have 3 variables, each one specified to lie in a specific interval here, right? The z is between 0 and 2, the y is between 0 and 2, and the x is between 0 and 2, right? Okay, so this is a somewhat simple, or a little too simple example, because the x, y, and z are all lying between values 0 and 2. That's because we're looking at a cube, but we'll see a slightly more complicated example in a while, right? Okay, so the z lies between 0 and 2, so that gives me my limits. The y lies between 0 and 2, this gives me my limits, and then the x lies between 0 and 2, and that gives me your limits, right? Okay, and remember how you did it for a double integral, right? How you did it for a double integral is you worked out the inside integral here first, right? So you integrated here with respect to y. Here, what you got was x y squared on 2, and you integrate e to the y, you got y, and then you put in your y values, y is equal to 2 and y is equal to 1, right? And over here, it's really just the same idea, right? Okay, so what you're going to do is you're going to first integrate with respect to z, right? So you're going to do your inside integral here, right? Okay, so the inside integral is the one with respect to z. I put brackets around it. And now I'm integrating this with respect to z, right? So integrate the 1 with respect to z, you get z. Integrate the 2z with respect to z, you're going to get z squared on 2. And you put in your z values. Z is equal to 2 and z is equal to 0. When you put in z is equal to 2, you're going to get 2 plus 4, which is 6, and then you subtract in 0, so you're going to get 6 minus 0, which is 6, right? Okay, so this inside integral over here would, this inside integral here, right? It just works out to be 6, right? And so you did the inside integral, but you have two integrations left over here, right? And you want to compare what we did for a double integral, right? Once you work out the inside integral over here, right? Once you work out your inside integral, what you're going to get is now you're going to have just one integration remaining, right? So over here, once I start, and in the triple integral case, once I work out the inside integral, right, then I have two integrals remaining, right? And now with these two integrals remaining, right, this is now just a double integral, right? Okay, so once you do your first integral here, and you work it out, you end up with a double integral, and now you should know how to work this out, right? So this is a double integral, right? And again, you're just doing the inside integration here, right? That's with respect to y. Integrate the 6 with respect to y, you get 6y. And you put in your y values, 2 and 0 here, right? Which will give me 12 minus 0, which gives me 12, right? Okay, and I still have one more integration to do. That's with respect to x, and this is now just normal integration. I integrate the 12 with respect to x to give me 12x, and I put in x is equal to 2 and x is equal to 0, and that gives me 24, right? Involving your mass density and volume, right? So let's go back to your simple case of where you have a cube of side length 2, right? And with constant density, right? Now, this is, if your constant density is 2.5, right, then your mass is going to be equal to 2.5 times the volume, which is 8, right? So it was 20, right? The mass was 20 for the example that I worked out, right? But if, however, the density is actually just constant at 1, right, then what you're working out over here is when the density is equal to 1, you just add rho is just going to be equal to 1. So the mass is just going to turn out to be equal, if the density is equal to 1, and the mass is just going to be the volume, right? Okay, so, and a similar idea holds for my triple integrals, right? If the density function over here, right, is just equal to 1, right, then when I do a triple integral of the 1 over here, the mass that I'm going to get is actually just going to be equal to the volume, right? So one more time, in your basic case, when the density is equal to 1, you get that the mass is equal to volume, right? In this case over here for your triple integrals, right, remember, if you do a triple integral of your density function over your solid region B, right, then what you're getting is the mass, right? What I'm saying is that if your density function is just 1, right, then that mass is equal to the volume just as it was over here, right? Okay, so I can write that down, right? If my density function is 1, right, then what I'm getting is that the triple integral of your function 1, where you're integrating over your solid region B, right, what you're getting is the volume of the solid region B. Okay, right, so this is useful for us, right? Probably not that useful because the solid regions that we would look at would be pretty simple, right? So you won't need to actually do a triple integral to work it out, right? But you can actually have more complicated regions than just a simple simple cube, simple solid cube here, right? So what I mean by that, right? Okay, so for example, this top limit of integration here, right, doesn't need, we're not going to do this in this class, right, but I'm just giving you an example, right? So this could, yeah, your top limit of integration, say, could be x or something like that, right? Right, and then also these limits of integration here, right, need not be right, need not be constants either, right? Okay, so here I have this solid region that is, right, that is some sort of pyramid over here, right? Okay, and I can in fact use this formula here, right? Using the appropriate limits of integration here. What I would have is x and 0 here, right? 2 minus x and 0 here, and 2 and 0 over here. And if I have 1 on the inside, then integrating the 1 with the appropriate limits of integration would give me the volume of the solid region here, right? Okay, so, but that's not within the scope of this class, right? But I still would like you to know, right, that if you do a triple integral of 1, right, over your solid region B, right, then what you're doing is you're getting the volume of the solid region. So the method that I just used to work out my triple integral over the solid cube was this Fubini's theorem for triple integrals, right? So if I have a solid rectangular box, right, and which would mean that the x is going to lie between constants a and b, the y is going to lie between constants c and d, and the z is going to lie between constants r and s, right? Then how I'm going to work out that triple integral is the triple integral is by putting your limits of integration in the appropriate places. So I'm going to integrate with respect to z, and then y, and then with respect to x, right? So if I'm integrating with respect to z first, I'd need the z limits, which would be the s and the r. Integrate with respect to y, then I'd use y limits d and c, and then x I'd use x limits a and b here, right? A on the bottom and b on top, right? Okay, and then what you do is you start integrating from the inside out, just as what I did in this example here, right? This example that I just did was pretty simple because, well, your limits of integration were all 2 and 0, right? But the process is you start working from the inside out, right? Okay, so this is called Fubini's theorem for triple integrals. You want to remember that we did a Fubini's theorem for double integrals when you had a rectangular region, right? And how you did it is you integrated, if you integrate them with respect to y, then x, right? You use your y limits here and then your x limits over here, right? So you're really just doing the same sort of thing but for triple integrals, and that's because you have, this is analogous to a rectangular region. So you have a rectangular region in two-dimensional space over here for your double integral, right? And here what I have is a rectangular box in three-dimensional space, and the working over here, right, to calculate the triple integral is actually analogous to what we had for a double integral over a rectangle here, right? Alright, so let's work out this example from the notes using the Fubini's for triple integrals that I just talked about, right? Alright, okay, so I'm gonna integrate this function x, y, z squared, right, over a rectangular box over here, right? So this is a solid rectangular box, right? And given that the x lies between 0 and 1, the y lies between -1 and 2, and the z lies between 0 and 3, right? Okay, so first thing you do is, well, this is your notation for your triple integral, right? And this actually tells you how we're going to evaluate it, right? So this is this right hand side over here. This is an iterated integral where we integrate in respect to z, then y, then x, right? Yes, in this particular case, right, I can actually switch the order of the integration, right? So I can integrate with respect to y, then z, then x, and so on, right? Provided I make sure I have the correct limits of integration for the appropriate variables, right? So you could rearrange this in 6 possible ways, right? So there's 6 possible ways of doing this integral, right? But typically, how I will do it and what should work for us is that we're going to integrate with respect to z, then y, and then x over here, right? Okay, so if I'm integrating with respect to z, I need the z limits, which would be 3 and 0. Then with respect to y, so I need my y limits, 2 and -1. And then with respect to x, which means I need x limits, 0 and 1 over here, right? Okay, so what I'm doing is I'm integrating over a rectangular box, and let's see what that box looks like. It doesn't really make a difference, but still. right? So this is what the box is going to look like, right? Alright, so you see in that the Z lies between 0 and 3, right? Okay, your Y is lying between -1 and 2, right? Okay, and then the X is lying between 0 and 1 here, right? Okay, so this is the solid box that we integrated over, right? Okay, and now once we have this setup over here, right, just do your integration, right? So you're working from the inside out over here, integrating with respect to Z first, right? And when I integrate this here, this x, y, z squared with respect to z, it's the same idea as what we had in the double integrals, right? So the z is the variable that you're integrating, and the x and y are just going to behave like constants when you're integrating with respect to z, right? Okay, so you're just going to integrate the z squared over here to give you z cubed on 3, and you put in your limits of integration, which would be 3 and 0, right? So when I put in the 3, I'm going to get 27 on 3, which is 9. And when I put in z is equal to 0, I'll get 0, right? So what I get is 9 times xy, right? Okay, so after I do my first integral with respect to z, what I get is 9xy, right? And now what I'm left with is just a double integral, right? In variables y and x, right? And you know how to do this, right? You integrate this with respect to y, you're going to get y squared on 2. You put in your y values 2 and -1, which would give me 36x on top here, alright? And you put in y is equal to -1, which would give me it's y squared here, so I'd get 9x on 2. So I have 36x on 2 minus 9x on 2, which would be 27x on 2 here, right? So I have to 27x on 2, and this is just normal integration here. I integrate, I get x squared on 4, right? And I put in my x values 1 and 0, which gives me 27 on 4, right? So my answer over here is 27 on 4, right? Okay, so that's the answer for your triple integral. If you wanted the interpretation and you regarded x, y, z squared as a density function for this solid rectangular box. In other words, from point to point, the density was changing according to this x, y, z squared, right? Then what you just did is you actually worked out the mass of this solid rectangular box, right? Alright, so the next type of solid that we want to integrate over is a cylindrical solid, right? And this is how we're gonna describe a cylindrical solid in set notation, right? Okay, so the easiest part over here is that the z lies between m and l, right? So what you do is you consider endpoints over here, right? So endpoints would be z is equal to l here, and z is equal to m, right? If we're in three-dimensional space, you should realize that z is equal to l, right? Is going to be a plane that's parallel to the xy plane, right? At height l over here, right? And z is equal to m is going to be a plane of height m over here, right? That's parallel to the xy plane, also parallel to this one, right? So what this means over here, that the z lies between m and l, right, is the solid object that I'm going to look at is going to actually lie between these two planes over here, right? And then the next thing that I have over here is x squared plus y squared is less than equal to a squared, right? Okay, so you want to remember that x squared plus y squared equal to a squared if we in three-dimensional space, right? What that defines for you is that this defines a cylinder that's centered around your z-axis of radius a, right? So your radius over here is a. This is a cylinder, right? Well, if you consider an equal to a squared, it's a cylinder of radius a that's centered around your z-axis. And less than or equal to a squared means that what you're doing is, for this cylinder over here, what you're going to do is you're going to basically fill it, right? So less than or equal to a squared means that you're looking at your cylinder of radius a, right? And then you're also considering the inside as well too, right? Okay, so this is a sketch of sort of cylindrical solid that we're going to be looking at, right? So let's probably look at a different sketch of a cylindrical solid specified this way in set notation, right? So this over here, this is a cylindrical solid that's centered around your z-axis, right? So this is centered around my z-axis here, right? The height, the z, is lying between z is equal to 3 and z is equal to 5, right? So the z is lying the cylindrical solid is lying between z is equal, the plane z is equal to 3 and z is equal to 5, right? The radius of this cylinder, right, is equal to 3. So if you project down, right, what you're going to see, I mean, this is sort of badly drawn, but this is supposed to be solid here, right? Okay, if you project down, what you're going to see is a disk of radius 3, right? Okay, so if you're looking at this here, right, and you're just thinking of it in the xy plane, right, then x squared plus y squared is less than equal to a squared, right? What that is giving me is that's giving me a disk in the xy plane, right? But what I actually have, right, is I actually have this x squared plus y squared less than equal to a squared, right, is an equation, well, an inequality in three-dimensional space, right? Okay, so this just by itself, right, to give you an idea, right, would be right, this over here by itself, right, x squared plus y squared less than equal to a squared, where this example, the a squared is equal to 3 squared, which is 9, right? This, in fact, is a cylinder, solid cylinder of infinite height, right? When you project down, project from your z-axis looking down, what you'll see is a disk of radius 3, right? That's if you're just regarding it in xy coordinates, right? But if you're regarding it in three-dimensional space, right, it's in fact a infinite solid cylinder, right? And what these, okay, so this part over here is an infinite solid cylinder, and what this part over here does for you is it chops it off according to two horizontal planes, right? So if I use, for example, z is equal to 3 and z is equal to 5, right? What I'm doing is I'm chopping my infinite solid cylinder, the center on your z-axis. I'm chopping it below over here at z is equal to 3 and chopping it above at z is equal to 5, right? Okay, anyway, so it's this type of cylindrical solid that we're going to be integrating over, right? And in order to do this, we're going to convert into cylindrical coordinates. Alright, so cylindrical coordinates, a point in cylindrical coordinates are specified using r, theta, and z, right? Now, all of these you saw already, right? Because this r and theta is the same r and theta from polar coordinates, right? In polar coordinates, what you're doing is you're working in a plane, right? So this, the xy plane, right? So this r and theta is relevant for the xy plane, right? And then you have a z, which is the normal z, which is height, right? In three-dimensional space, right? Okay, so say let's look at an example, right? So I have this particular point, this orange point over here, right? And this is a point in three-dimensional space, right? Now that particular point, you can specify the point by using x, y, and z, right? Okay, and you see in the z there already, right? The z is the height, right? So z is just normal height over here, right? And the x, that point over here, so this point, if I project down, right? Well, what's the x, right? The x is, for the point over here, the x is, if I project down onto the xy plane and I drop a perpendicular over here, the x coordinate for this particular point would be over here, and then the y coordinate would be over here, right? Anyway, so this really shouldn't be anything new, right? Any point, you have x, y, z coordinates, and you should be able to plot a point in given x, y, and z coordinates, right? what we're looking at here is a point now in cylindrical coordinates, right? Okay, so what I have is r, theta, and z, right? And this graphic over here is supposed to illustrate what the r, theta, and z is going to be, right? Okay, so what the r is measuring is okay, what the r measures for you, right, is if I have this point over here, right? So this is the point that I'm interested in. What the r is I take this point over here and I project it down onto the xy plane, right? And I measure the distance from the projection to the origin, right? Okay, so the point I project down onto the xy plane, right? So when I project it down onto the xy plane, what I do is in the xy plane, I measure the distance from the origin, right? And that is going to be your r over there, right? Okay, now you could think of this as being, and then, okay, so this is r over here, and since we're already here, right, what the theta is this angle here, right? Theta is this angle, right? And you want to notice what you could do is you could just swing this. Okay, so this is the original point over here projected down onto the xy plane, connected to the origin by this line that has length r, right? And what I could do is just swing this around the origin by angle theta to get to this point over here, right? And this distance is also r, right? Or if you want, this is an arc of a circle, which means that this radius here is equal to this radius here, right? Which is r, right? Okay, so one more time, right? I have this point over here to get the r, theta, and z, right, associated to this point. The z is just a normal z, right, which is height of the point, right, above the xy plane, right. To get the so this is your height over here. To get the r and the theta, right, you see that they label this angle over here as theta, right. To get the r and the theta, what you're doing is you're taking your point over here and you're projecting it onto the xy plane. So what we could do is, with this software, we can project down onto the xy plane, right? Okay, and with this point here, the projection, right, the theta is the angle, this angle over here, right? Okay, so with your point over here, you take your point and you connect it by a line to the origin, right? And the angle at this line makes with your x-axis, right? This is your theta over here, and the distance from here to here is r, right? So the r and theta is just the same. If I had this point and I wanted the r theta polar coordinates, it's the exact same r theta polar coordinates. So at this point in time, if you project down into the xy plane, right, what you're doing is you're using r theta, and that's the same polar coordinates that you had that you know from before, right? Okay, and this graphic sort of does it in a nice way, right? Uh, Interpreting what the r, theta, and z is, right? So okay, so first what it does is to locate it determines what the r is, right? So it slides along the x-axis, right, by a distance of r, right? And then once you do that, right, then you rotate in the xy plane by an angle of theta. And then once you do that, right, so this at this point, what you have is the projection at the point, right? And then you need to go up by the height over here, which is the z, right? Okay, so that's the point in r theta z, right? And the r theta z in this case is this theta is equal to 3, right? This angle is pi on 4, right? And the height over here is 4, right? So this is 3 pi on 4 and 4, right? So the r is 3, the theta is pi on 4, and the z is equal to 4 for this particular point, right? Okay, and I can reverse this, right? So this is your point, right? Coming down like this, projects onto the xy plane over here, right? And here what you're doing is, now that you're in the xy plane, you could just consider your point in the xy plane and work out the r theta in the normal way, right? And that's what they're doing for you, right? So this angle over here is theta, and they move back by angle theta to get to the x-axis. and that's your r over here, right? And the r is the length in the xy plane, right? And by projecting points onto the xy plane, you get your conversion between cylindrical coordinates and xyz, right? And in cylindrical coordinates, the z is just the same as the normal z, right? So this is what the z is equal to z is, right? And the r and the theta, as I said, right, have the same interpretation in the xy plane as polar coordinates, right? So your conversion between the x and the y is the same as what you had in polar coordinates, right? So this here is your conversion between x, y, z and polar coordinates, right? If you want, we could take a look to see where we get the r cos theta and the r sin theta, right? Okay, so I have this point over here, right? That point is a point in three-dimensional space, right? Okay, and I want to get the x, y, and z, right? So this is the r over here. The r is the distance from here to here, right? This is the r. Unfortunately, I don't know if you're seeing it, right? They call in this row this in this software in this diagram, but the notation that we will use over here is r, right? So the r is from here to here, right? So this is the r. The z is the height from. This is the point that we're considering, and if we project this point down onto the xy plane, this height over here, right? That is the z, right? And the theta is this angle from here to here, right? Okay, right. So this is the point that we're interested in, and we're trying to get an idea of the conversion that the x is equal to r cos theta, the y is equal to r sin theta, and the z is equal to z, right? So this z here is if you have r theta z, if this point has coordinates r theta z, right? This z here is your normal z, which is height, right? Okay, and how you get the r cos theta and the r sin theta, right? What we could do is we could project. Okay, so this is the point over here, and what I'm going to do now is I'm just going to look down, right? Get a plan view, in other words, project into the xy plane, right? Okay, so this is the point when I project down onto the xy plane. This is your angle over here. The angle over here is theta, right? And this would be the x for the point, right? And the x you see in is just, if this is theta over here and this length over here is r, right? Then your x is equal to r cos theta, right? And the y is equal to r sin theta, right? Okay, so just using normal right angle triangle and your definitions of cosine and sine, right? Okay, so we saw this, we talked about this cylindrical solid over here, the x squared plus y squared less than equal to a squared, right? What that is that's an infinite solid cylinder of radius a. And what the z line between m and l means, it means that what you're going to do is you're going to take two horizontal planes, z is equal to m, z is equal to l, and you're going to cut the infinite solid cylinder, right? And you're going to take the piece that lies between the plane z is equal to m and z is equal to l, right? So this is your cylindrical solid expressed in x, y, z coordinates here, right? And now what we want to do is you want to express it in cylindrical coordinates, right? Okay, so right, well, as I said, in cylindrical coordinates r theta z, right? The z has the same meaning as what it has in x, y, z, right? It's the same z, right? Okay, so this z line between m and l, right, is the same. In order to get to describe the z over here, you just use the exact same inequalities here, right? Okay, so this cylindrical solid, it lies between planes z is equal to m and l, right? And likewise over here in cylindrical coordinates, it's going to lie between planes z is equal to m and z is equal to l, right? Because the z has the same meaning, right? Alright, and then what I need to do is I need to convert this piece over here, x squared plus y squared less than equal to a squared, right? I want to convert that into r and theta, right? But converting that into r and theta is, remember the r and theta, it has the same, r and theta in cylindrical coordinates has the same meaning as what it has in polar coordinates, right? Okay, so the x squared plus y squared less than equal to a squared. What you're doing now to convert into r theta, you're just looking at it in the plane, right? When you look at it in the plane, what you have is you're going to have a disk of radius A, right? And by now you should know that if I have a disk of radius A, right, a disk of radius A, you can express in polar coordinates. Disk of radius A, such as this here, right? Okay, where x squared plus y squared is less than or equal to a squared, right? You express in polar coordinates, right? So you see an example of what we did here before, right? When we were doing double integrals in polar coordinates. X squared plus y squared less than or equal to 1 squared, right? Is a disk of radius 1, right? Where the r lies between 0 and the radius, which is 1 over here. And the theta lies between 0 and 2 pi, right? So likewise, this x squared plus y squared less than or equal to a squared, right? To describe this part when you project down into the xy plane, right? So when you project your solid cylinder down onto the xy plane, right, what you're seeing is a disk of radius a, right? In this case, the a is equal to 3, right? Okay, right, your disk of radius a we can express in r theta, right, as the r line between the r line between 0 and a, right, and the radius is a, right, and the theta going between 0 and 2 pi, right, just as what we did in just normal polar coordinates. Right, so our method for evaluating a triple integral over a cylindrical solid such as this one here, right, is by converting to cylindrical coordinates, right? Okay, so this is a cylindrical solid. Once it's of this form, as once your set description over here in terms of xy is given like this, right? Then in cylindrical coordinates, what that means is the r lies between 0 and a, the theta is between 0 and 2 pi, and z lies between m and l, right? Okay, so to work out your triple integral over a cylindrical solid, right? What you're doing is you're using a conversion here, right? So the x is going to convert to r cos theta. The y is going to convert to r sine theta. The z just remains the same, right? You're going to have this extra r outside over here. And now you're going to integrate with respect to your cylindrical coordinates, right? Which would be the z, the r, and the theta, right? And your limits for the z, r, and theta come from, well, they come from either here or here, right? So for the z, right, you're seeing that the z lies between m and l here, right? The z lies between m and l, right? And this over here is saying that if you project down onto the xy plane, you have a disk of radius a, right? So the r lies between 0 and a, and the theta goes between 0 and 2 pi, right? Or it's easier if you do your conversion and you write out your conversion of the v, you express this v over here in terms of cylindrical coordinates. In which case you can now just read off your limits, right? So for the r, it's between 0 and a. And for the theta, it's between 0 and 2 pi, right? Okay, so this is your setup over here, right? This would be how you'd integrate over a cylindrical solid. You convert the x to r cos theta, the y to r sine theta, to z to z. You have an extra r over here. You're going to be integrating with respect to z, r, and theta. For the z, you take for the limits for the z, r, and theta, you take them from this set description over here for your cylindrical solid. Okay, so this is how you're going to integrate do a triple integral over a cylindrical solid. You're going to do a conversion to cylindrical coordinates. And if you want, you can compare it to what you did when you convert in polar coordinates, right? So here, what you had was you had a double integral, right? And what you wanted to do is you want to integrate over a polar rectangle, and you do that by converting into polar coordinates, right? So why I'm mentioning this is that there's similarities between a conversion here, right? Here, what you did is the x was r cos theta, the y was r sine theta, right? You put in the extra r over here, and then the limits of integration came from your description of your region R as a polar rectangle, right? So you're able to figure out the limits for R here and for theta over here, right? And you're doing something similar across here, right? Converting x is r cos theta, y is equal to r sine theta, and z is equal to z, and so on, right? Okay, so you should really, if you're probably not happy with this, you should just recall what you did in your conversion to polar coordinates, and it's the same idea, right? Or a very similar idea, right? Right, so let's consider this example here. This is from December 2016 past paper on the website, and the solutions are also on the website, right? Okay, so I want to do a triple integral over this cylindrical solid over here, right? Where what I'm doing is I'm integrating the function x squared plus y squared, right? Now, in order to do this, what I'd need to do is I'd need to convert to cylindrical coordinates, right? Okay, so you're going to convert to cylindrical coordinates and you're using this formula over here, right? So the x is going to change to r cos theta, the y is going to change to r sin theta, and the z is going to change to z, right? Okay, so right, so you're using this formula here, right? And you're going to convert the x to r cos theta and the y to r sin theta, right? And notice over here what you'd get is r squared cos squared plus r squared sin squared, right? Which would mean that you'd eventually end up with a r squared over here. I think I talked about this already. The x squared plus y squared in polar coordinates is equal to r squared, right? Okay, and yeah, I'm dealing with cylindrical coordinates, but the r and theta mean the same thing as they do in polar coordinates, right? So, or if you want, what if you use x is equal to r cos theta and y is equal to r sin theta, and you work it out manually, r squared cos squared plus r squared sin squared would give me r squared over here, right? So the conversion going from here to here, right? What I'd get is an r squared, right? And then also what I need to do is I'd need to express this over here. I need to figure out what the r theta and z are going to be for this, right? So I'd need to express this in this form over here, right? I want to express my cylindrical solid in terms of cylindrical coordinates, right? Okay, and that is done over here, right? Okay, so in same cylindrical solid written in cylindrical coordinates, right? The z lies between 0 and 5, so the z lies between 0 and 5. And this part over here is just telling you that you have a disk of radius 3, right? Or when you project onto the xy plane, you have a disk of radius 3, right? Okay, so or this just by itself, if you forget about the z line between 0 and 5, and you forget about the fact that you're projecting, right? This by itself, regarded in three-dimensional space, right, is a cylindrical solid, right, of infinite length of radius 3 that's centered around your z-axis, right? Anyway, so for this over here, right, what we need to do is figure out the r limits and the theta limits, right? And the radius over here is this 9 is 3 squared, so you get this 3 over here. And you're going straight around your z-axis, so the theta is going to go between 0 and 2 pi, right? So this is your cylindrical solid expressed in terms of x, y, and z, and this is it expressed in terms of r, theta, and z, right, in cylindrical coordinates, right? So I'll need this, right? Okay, so what I'm using is I'm using this conversion formula here to work out this problem, right? And so far we saw that x squared plus y squared is going to be equal to r squared, right? And we can figure out what the limits of integration are because we did that here, right? By expressing v in terms of cylindrical coordinates, right? Okay, so let's look at the answer now, right? Right, so I'm using my conversion. The x squared plus y squared is equal to r squared, right? Right, part of your formula in the conversion is you're going to have this extra r outside here, which is this extra r. You're going to be integrating with respect to r, theta, and z, right? Well, okay, here what I did is, okay, so this is z, r, and theta. This is expressed in terms of z, r, and theta, right? And here I did it with respect to r, theta, and z, right? And I can do it that way provided I keep the correct limits of integration, right? Okay, so here I have r squared. I have the extra r outside here, right? The right, this x squared plus y squared worked out to be equal to r squared, right? I have my extra r outside here, and I need my limits of integration, right? But the limits of integration come from expressing v as a polar rectangle, right? So you see in here that the r lies between 0 and 3. So the limits of integration for the r would be 0 and 3, right? The limits of integration for the theta would be 0 and 2 pi, right? And the limits of integration for the z would be 0 and 5, right? Okay, so I have it set up over here, right? Going from here to here, you're using the conversion formula, right? The x squared plus y squared would convert to r squared, right? You'd have an extra r, right? And now you integrate with respect to the variables in the cylindrical coordinates, which would be r, theta, and z, right? Okay, and if I decided I'm going to integrate with respect to r, theta, and z in that order, right? Then I'd need the corresponding limits of integration here, right? Which I wrote down, right? And now once you have this, this is now just similar to what we did for a triple integral in xyz coordinates, right? You're just going to work from the inside out, right? So first thing you'd want to do is multiply this r with the r squared to give me r cubed, right? And then when I integrate the r cubed, I'm going to get r to the 4th on 4, right? Right. Once I get the r to the 4th on 4, right, what I do is I put in my r values, which are 3 and 0, right? And 3 to the 4th is 81, so I get 81 on 4. If I put in 0 here, I'm just going to get 0, right? So substituting the 3 and 0 gives me 81 on 4 minus 0, which is just 81 on 4, right? And now what I'm left with is a double integral here, right? And you integrate with respect to theta, which would give me 81 theta on 4, and I put in the 2 pi on the 0, right? Which would give me 81 times 2 pi divided by 4, right? Which is going to be the 2 and the 2 pi will cancel with this 4 over there to give me a 2 on the bottom. So I'm going to get 81 pi on 2, right? Okay, so I have the 81 pi on 2, and now what I do is, the only thing left to do is to integrate with respect to z. So if I integrate with respect to z over here, right, I'm going to get 81 pi z on 2. And then I put in the 5, and I put in the 0, right? So that would give me 81 times, when I put in the 0 here, the 0 would just give me 0, right? So I would get, the only thing non-zero I would get out of this is when I put in the z is equal to 5, right? So I'm going to get 81 times 5, which is 405 times pi divided by 2, which is the answer, right? Okay, so there's some details missing in this. You can always just work it out and fill them in, right? So let's see our next example of evaluating a triple integral of a cylindrical solid, right? So a cylindrical solid is described in xy coordinates over here, right? All right, and how we're going to work this out is you're going to use this formula, right, where we convert to cylindrical coordinates. So the x will be, you substitute r cos theta for x, r sin theta for y. You're going to have an extra r when you do your conversion, and then you need to get your limits of integration by expressing this region over here in cylindrical coordinates, right? Okay, so here's the working, right? I have z is equal to x squared plus y squared, right? Okay, so you're going to convert, right? The x, well, you substitute r cos theta for the x, right? So you get r squared cos squared. Substitute r sine theta for the y, which give me r squared sine squared, right? I have my extra r out in front, right? The solid cylinder B, right? You'd need to convert, express it in polar coordinates, which is done over here, right? Here the radius is 2, right? So you see your radius is 2 over here. So the r is going to lie between 0 and 2. Right, this over here, right, when you project onto the xy plane, you're going to get a disk of radius 2, right? and you get in the entire disk, which means that it's theta is going to go between 0 and 2 pi, right? Okay, and the z just goes between 0 and 3, and that's just the same z going between 0 and 3, right? Okay, so I have the the limits for the r, theta, and z, right? And I have the limits for the r, the theta, the r, theta, and z, right? Okay, so here the z limits are L and M, the R limits would be A and 0, and the theta limits would be 2 pi and 0, right? So the conversion process over here is I need those limits for the R, theta, and the Z, right? And I just found them, right? They, over here, right? Okay, and also, as I said, the x squared plus y squared, well, you're going to get r squared cos squared and r squared sine squared, right? And that would reduce down to r squared over here, right? I have the extra r out in front, right? So what I have over here is z r squared times r, which would give me z r cubed, right? And here I'm integrating with respect to z theta, then r, which is, right, a different order from what I stated over here, right? But it doesn't make a difference once you make sure that you use the appropriate limits, right? So for this middle r over here, you'd need r limits, and for the outside theta, you'd need theta limits, right? Okay, and in this case, right, what we're using is we're using right, we integrated with respect to z, theta, and r, right? So your limits of integration for the z would be 3 and 0. Limits of integration for the theta would be 0 and 2 pi, and the limits of integration for the r would be 0 and 2, right? Okay, so once we have that set up, now you just clean this up a little bit. You're going to have the z r cubed over here by multiplying this r squared by r, right? And then you start working out your triple integral, right? Which means that you're going to do your inside integration here first, right? And here I'm integrating the inside over here with respect to z, right? So the r cubed is just a constant for me, right? So I'm going to get z squared on 2, right? And then what I'm doing is I'm putting in z values, right? Z is equal to 3 and z is equal to 0, right? Okay, so when I put in the z is equal to 3, I'm gonna get 9 on 2, and when I put in the z is equal to 0, I'm gonna get 0, right? So what I get is 9 on 2 r cubed here, right? Okay, and now this over here, I'm going to integrate with respect to theta, right? So this is a constant as far as the theta is concerned. So I'm going to get 9r cubed on 2 times theta here, right? And then I put in the theta values, which are 2 pi and 0, right? And when I put in the theta is equal to 2 pi, right, what I will have is that the 9 on 2 against the 2 pi would give me 9 pi, right? Okay, and putting in the 0 just gives me 0, right? So I have 9r cubed times pi, right? And then finally what I need to do is I need to integrate this with respect to r, right? When I integrate with respect to r, I'm gonna get 9r to the 4th on 4, right? And I put in times pi, right? So I get 9r to the 4th on 4 times pi. The pi is literally a constant. So the 9 and the pi are just constants. And then you put in the 2 and the 0, right? And when I put in the 2 here, I'm going to get 16 on 4, which is 4, right? And 9 times the 4 is 36, right? So I get 36 pi. I'm putting in r is equal to 0, just gives me 0. So I get 36 pi minus 0, which is just 36 pi.